So in the previous video or the previous section, we have seen about the gates, which where we have learned about the all the different types of gates which we'll be using, AND gate, OR gate, NOT gate, XOR, XNOR, NAND NOR, and we saw some delay related things and their properties as well. So kind of a basic thing which we have seen in the previous section. Now we are moving and extending the idea. We are adding more knowledge towards those gates and how things will be used in the future sections. That is what we'll be learning. Okay, so here we'll be basically learning about the Boolean algebra and the reduction techniques. So what you can expect in this section is basically we'll be looking at the Boolean algebra, Boolean laws, Boolean theorems, and how it will be used to minimize a function. Okay, a function will be representing some digital systems output. Okay, and how the circuit will be made, small things we will see, so that it will build a base on which we'll be looking at future sections. Also we'll be looking at k-maps, Quine-Maklenski method, and all those things which are basically the reduction techniques. Boolean algebra is also a reduction technique, but it fails after some times. I mean, it becomes like a tedious thing. Okay, it doesn't fail means like it becomes a tedious thing to use it, so that we come up with better reduction techniques, which are k-map and Quine-Maklenski methods. So those things will revolve around. We'll see some extra properties as well. The more time we'll be spending on k-map actually, which is much more important, and this will be the flow actually, and I'll keep on adding new stuff. Also we'll be looking at different types in which we can represent a Boolean function, which we are representing with f or y, right? So those things, how we can represent in different fashion, we'll be looking at that also. Okay, so these will be the structure. So let's start. So the Boolean algebra and the reduction technique. So Boolean algebra, what this means is it represents the logical operation, just like plus, minus, multiply, divide, you do know. So in logical terms, if you perform any algebra, that is called as Boolean algebra. To perform those operations, you need Boolean laws and Boolean theorems. Okay, so that we'll be looking at first. So what are those Boolean laws and theorems? We'll be starting from here and here like this, and they will be based on some axiom. Axiom is basically a definition without proof. You take it as it is. Okay, you don't ask for a proof of these things. That's what axioms are called as. They are basically definitions which you don't ask proof for, and you use that as it is. Okay, you think of someone has done the work of proving this axioms, and now you are given with it and you have to use it. Okay, so using these axioms, you will be making Boolean laws and Boolean theorems, and by using Boolean laws and theorems, you will be able to reduce a function. Okay, so we'll see that. So what are those axioms? First of all, it is OR operation, AND operation, and NOT operation, which you have already seen. So what they are, in OR operation, these are the four operations. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. This is how it is defined. You have to take as it is. In AND operation, it is 0 dot 0 is equal to 0, 0 dot 1 is equal to 0, 1 dot 0 is equal to 0, 1 dot 1 is equal to 1. And in NOT operation, if you have 1, the complement of 1 is 0. If you have 0, the complement of 0 is 1. This is how it is defined. Okay, these are called the AND, OR, and NOT axioms. Now using this, you have a lot of laws which will be used in minimizing the function, and also theorems. Okay, so one by one we'll be looking at them. So the first one is complement laws, which is similar to NOT operation only. So 0 bar if you will do, you'll be getting 1. 1 bar if you'll be doing, you'll be getting 0. So these are two laws. Third law is means like within complement laws, the third one is if a is equal to 1, a bar will be equal to 0. If a is equal to 0, a bar will be 1. Okay, so the generalized version of these two guys. Okay, and if you will take a double complement of a variable, a double bar, if you will do, the variable itself will come. Okay, so these are 1, 2, 3, 4, 5 complement laws. Okay, so these two are called as complementation law, and this is called as a double complement law or involutionary law. This is very important name. Okay, it is used a lot of time. So the way to remember all this is to use them in reducing the function. The more you will use it, the better you will remember it. Okay, if you will try to directly remember it, then you won't be able to remember it for a long time. So the better way is to keep on doing questions on function reduction, and you will be able to remember them. So here in Boolean algebra, no fractions, no negative number, no square root, no algorithms, only ones and zeros you talk about. So A can take value 1 or 0, logic 1 or logic 0, not the voltages. Logic 1 will be represented by 5 volt or maybe some 10 volt or 1 volt, it doesn't matter. Or logic 0 can also be represented by 0 volt, minus 5 volt, minus 3 volt, it doesn't matter. We are calling it together as logic 1 and logic 0. Okay, so that's how we work in digital. Then second law is AND law. AND law is defined in 4 ways. So A dot 0 is 0, A dot 1 is A dot A is A, and A dot A bar is 0. So this is sometimes called as null law because 0 is coming. Here it is identity law because multiplying it with 1 is giving you same variable. So identity law. These are basically AND law only. Okay, so this was basically NOT law, and this is AND law, and OR law also. You can see that A plus 0 is A plus 1 is 1, A plus A is A plus A is 1. A plus A bar is 1. Okay, these are the laws which are made. Okay, you don't means like this is based on these 3 guys. Okay, so you can understand these are very easy stuff, and we have seen in the previous section as well. So this is called null law, this is called identity law. Another type of law you can see here which we have seen, commutative law. Commutative law is basically 2 types are there, 1 and 2. Okay, so first one is A plus B. If you do, it is same as B plus A. Okay, either you or B with A or A with B, both are same thing. Okay, that's what it is trying to tell you. You can prove it via truth table. This is what the truth table of A plus B and B plus A is. So A, B are the 2 variables, so input variables. So how many combinations? 0 0 0 1 1 0 1 1, 4 combination. 2 to the power 2, this 2 is representing A and B, and 2 to the power 2 is representing 4, which is these 4 guys. And you can see if you will do A plus B, you will be getting 0 1 1 1. And you can see this is same as this guy, right? If you will take B first and A later on, 0 0 0 1 1 0 1 1, the sum will be same. B plus A is also same, 0 1 1 1. You can see this column and this column is same. So that's why it tells you that visual representation, you can see that if you or the A with B or B with A, you'll be getting same thing. Okay, so that's the commutative law. And you can extend it to multiple variables, so you can add more variables, A plus B plus C. So if you'll add C, A with B and B with C, it is same as adding A with C and then B. You can shuffle it, means like they are trying to tell you. So B with A then C, or C with A then B, you can shuffle it, means like there is no issue. That's what it is trying to tell you. Similarly, you can do in XOR, XNOR, NAND NOR. These are also, we have seen that, right? You can extend the idea to multiple variables. So A XOR B is same as B XOR A. A XNOR B is same as B XNOR A. A NAND with B is same as B NAND with A. A NOR with B is same as B NOR with A. So commutative property is followed by all the gates basically. This we have seen in the previous section. We'll be looking at some new laws here. This is the first version, which is OR type of thing. Okay, AND type of thing is A dot B is equal to B dot A. It tells you that if you AND B with A or you AND A with B, both are same thing. Okay, it looks same, but things may get different in associative. You have seen previously. So A dot B if you do, or B dot A, it is same thing. You can confirm it by truth table. You can see here. So AB is 0 0 0 1 1 0 1 1. Here BA is 0 0 0 1 1 0 1 1. So if you do A dot B, so 0 dot 0 is 0, 0 dot 1 is 1 is 0, 1 dot 0 is 0, 1 dot 1 is 1. So this is based on AND law, or you can say this operation or this operation, whatever you can think of. Okay, and same thing you will be getting here as well. B dot A if you will do 0 0 0 1, you can see this column and this column is same. visual representation, you can see this is AND gate, this is AND gate. A dot B if you do, or B dot A, it is same thing. Okay, they are equal. So this is the visual representation, this is the truth table verification of this law. Okay, so two laws are there within commutative. One is OR type, one is AND type. Okay, this can also be extended. A dot B dot C if you do, B dot C dot A if you do, C dot A dot B if you do, or B dot A dot C you do. All are same. All will give you same result. All will have same column. That's how you should think. Okay, so this is the commutative law, AND OR law, complement law, based on axioms. The fifth one also you are aware of, associative law. Okay, which is A plus B if you do first, and then the resultant you'll do the addition with C, you'll get something, right? And if you will do B plus C first, and then the resultant you will add it with A, that is same as what you have achieved here. Okay, so that's the idea. So bracket thing you'll solve first, and then you add the rest one. It turns out that associative laws tells you that these are same stuff. So visual representation wise, if you will see, this is OR of A and B first, bracket wise, and then the resultant is ORed with C. So you are getting A plus B plus C, but first you did this two guys ORed, which is same as B, C getting ORed first, and then the resulting intent is getting ORed with A. It is same as A plus B plus C, but bracket was here. So the difference between these two guys are the order has been different. B and C first you ORed, and the resultant is ORed with A. Here A and B is ORed first, and the resultant is ORed with C. It turns out associative law tells you that both are same. Okay, you can extend this idea to multiple variables. A plus B plus C plus D first you do, and then you OR it with A. Or A plus B plus C first you do, then OR it with D. Or you do A plus B first, and then C plus D, and then a resultant you add together. They all will give you same result. They all are equal. Okay, that's the idea here. But here there is a catch here, which we have seen in the previous section also, that recall NAND and NOR does not follow associative law. Okay, here everyone follows commutative law, but here associative law is not followed by NAND and NOR. You have seen that A dot B bar you do, and then the resultant whatever you are getting, if you NAND it with C, it is not equal to B ANDed with B NAND with C, and then the resultant NANDed with A. Okay, similarly for NOR guy, so they are not equal. So that is something you should always remember. Whereas XOR, if you will see, XOR can also be written in this fashion. So A XOR B you do first, and then the resultant you do it with C, or you XOR B and C, and then the resultant XOR with A. They both will give you same answer. Okay, similarly for XNOR, you can see they will give you same answer. A XNOR B you do, and then the resultant XNOR with C, or B XNOR C you do, and the resultant XNOR with A, you'll be getting same stuff. Okay, so that's the idea. Similarly, so everyone follows associative, but NAND and NOR does not follow associative, whereas here commutative is followed by all of them. So here you can check it. This is the way. So A plus B plus C you do. So here you can see A, B, C are the three variables. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are the combinations. First you do A plus B. This you will be getting. So first column and second column you add. So 0 plus 0 is 0, 0 plus 0 is 0, 1, 1, 1, 1, 1, 1. This is OR law, or you can say the axiom or axiom. Similarly, the resultant what you are getting, you OR it with C. So you add these two columns. These two columns means so 0 plus 0 is 0, 1, 1, 1, 1, 1, 1, 1. So this is one truth table. Okay, the left hand side. The right hand side, if you will do, what will be the change? First you will add BC. So 0, 1, 1, 1, 0, 1, 1, 1. So this is the column. And if you will do B plus C plus A, means like then you add this guy with this column, right, like this. So you'll be getting 0, 1, 1, 1, 1, 1, 1, 1, right? That's what you are getting. So if you check this truth table and this truth table, they both will give you this same column. Okay, so that's the meaning of this expression. So hopefully you have understood via truth table also. Second form of this associative law is AND type. So you can see A dot B first you do, and then resultant, if you will AND with C, you will be getting the same thing when you will AND B, C, and then resultant you will AND with A. Okay, so both are same expression you can think of. So the expression visually you can see in this fashion. So here A and B are ANDed first, and the resultant is ANDed with C. Okay, here A is B and C are ANDed first, and the resultant is ANDed with A. So here you are getting A dot B first, and then the resultant is getting ANDed with C. Here you are getting A dot B, B dot C first, and then resultant is getting ANDed with A. Okay, so this is the visual representation. They will give you same thing. Truth table wise, if you want to see, this is how it will look like. So ABC is there, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. A dot B you do first. So this column and this column multiply. So 0, 0, 0, 0, 0, 0, 1, 1. That's what it is written. Now the resultant you multiply with C. So you'll be getting 0, 0, 0, 0, 0, 0, 0, 1. Okay, so last guy will be only 1. So this is one truth table. Similarly, left hand side you have calculated, right hand side also you can calculate. So this thing will be same here. ABC 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now you are calculating B dot C first. So these two columns you multiply first. So 0, 0, 0, 1, 0, 0, 0, 1. Okay, that's what you are getting here. And now whatever the resultant you are getting, you AND with A. So you will be getting 0, 0, 0, 0, 0, 0, 0, 1. You can see this is the column you are getting. And if you will observe, this column and this column is same. That's why they are equal. So this is truth table version, and this is the visual representation. Okay, and you can extend the idea. You can first AND BCD. If you have 4 variables, BCD you AND it, and whatever the result you are getting, you AND with A. Or you AND ABC first, and resultant you will AND with D. Or you AND AB separately and CD separately, and whatever the resultant you are getting, you AND them together. In all the cases you will be getting same answer. Okay, so that's the idea. That's how you extend it. So hopefully you have understood. This was same as previous what you can say, previous section type, but we'll be extending the laws, means like more laws we will be looking here. That's the idea. So we have seen complement and or law, commutative and associative. Okay, they all have they both have 2 forms here. Here you can see, and here you can see. Sorry, here and here. Okay, and here you had how many? 4 types. Here you had 4 types. Here you have 5 types. Okay, no need to remember all this. Okay, you will automatically remember if you will use them in reducing the function. Okay, so this is the idea. Next in next video we'll be looking at more laws. Okay.